Hi guys, this is Mr. Robeson. Welcome back to Calculus. Today we are looking at Rolle's theorem, the mean value theorem, and some applications of the mean value theorem. All right, if it has an abbreviation, it's important. So MVT, mean value theorem, important. All right, so first off, Rolle's theorem. So Rolle's theorem is actually not tested on the AP exam. So I just want to point that out. It's not on the AP. But it's actually where the mean value theorem comes from. So that's why we're going over Rolle's theorem here. So Rolle's theorem has three conditions. So first, we need our function f to be continuous on some closed interval, so including both endpoints. We'll need it to be differentiable on the open interval, so it doesn't matter if it's differentiable at the endpoints, but in between it needs to be differentiable. And we need the two endpoints to equal each other. So if we plug in A and plug in B, we get the same value. All right. Then what Rolle's theorem says is that there is some other number c in this interval where the derivative at that point will be 0. In other words, we're going to have a relative min or a relative max that's a nice smooth hill. Like it'll be the top of a hill or the bottom of a valley. Something will happen. So as long as these two endpoints are the same height, so at this point they're both at D, and this is differentiable and continuous. See, it's continuous. It's a nice smooth curve. It's differentiable. We can take its derivative everywhere here. Then we get some 0. So we have f prime of some c equal to 0. All right. If any of these conditions fails, like here it's continuous, you can draw it. It's a nice smooth curve, but it's not differentiable. All right, we cannot take the derivative at a corner, so it's not differentiable there. So that means Rolle's theorem does not hold here. Rolle's theorem will not work. Rolle's theorem, a no-no. All right, so that's kind of the idea here. So we got the slope will match the slope here. That's what Rolle's theorem is saying. All right, so applying Rolle's theorem, let f of x equal x squared times the quantity x squared minus 2 applies Rolle's theorem to find all values of c in the interval from -2 to 2 that satisfy Rolle's theorem. All right, and this is what Max is doing right now, sleeping on multiple pillows on the couch. All right, so to check Rolle's theorem, we need 1 to show that f of x is continuous on the closed interval, so from -2 to 2. Well, is it? Now, this is just a polynomial. Polynomials are continuous. So yes, that works. 2. F is differentiable. I was going to say f prime exists, but f differentiable on the open interval. So from -2 to 2, we don't care about the endpoints now. So can we take the derivative of this guy and then plug in every point between -2 and 2? Yeah, we can. All right, in step 3, we want to know what's f of -2 and what's f of 2, and are they equal to each other? So if we plug in -2, actually this is an even function, so yeah, they are going to be equal to each other. But if we plug in -2, we're going to get 4 times 4 minus 2, which is 8. If we plug in +2, we're going to get 4 times 4 minus 2 also, which is 8. So these two guys are equal to each other. So Rolle's theorem checks out. So that means f prime of some c will equal 0 for -2 is less than c is less than 2. C between those two. So somewhere in there will be a relative min or a relative max, maybe even both. Could happen more than once. Let's check out the graph and see. So it doesn't say we actually have to find Rolle's theorem to find all the values. Yeah, I guess we have to find them. But let's take a look at the graph here. All right, so here's the graph, and we have 1, 2, 3 different spots. If we wanted to actually find it, we could take the derivative. The easiest way to take the derivative here is first to distribute the x squared. So we get x to the 4th minus 2x squared. Take the derivative. F prime would be 4x cubed minus 4x. If we set that equal to 0, we can factor out a 4x. We're left with x squared minus 1. This will give us 0. This will give us plus and minus 1. So yep, we do get 3 values. These are all in this interval where we have the derivative equal to 0. Rolle's theorem told us they existed, so we can actually find them. There they are. All right, now the more important one, the mean value theorem. So now we only have 2 conditions to check. We need the function f to be continuous and differentiable. All right, same 2 conditions. We just leave off the 3rd condition. continuous on the closed interval, differentiable on the open interval. All right, and mean value theorem is actually a little bit stronger than Rolle's theorem, but people came up with Rolle's theorem first. All right, so the mean value theorem says that the derivative at some point c in the interval will equal the slope between the two endpoints. So here's our one endpoint, a, f of a. Here's our other endpoint, b, f of b. We find the slope of this line. So the slope of this line will be exactly this. So the height is the change in the y values. So f of b minus f of a is the height. The length is just going to be b minus a. So our slope is exactly this. So this is the slope between the endpoints, and the derivative will just equal that slope somewhere. So somewhere along this curve, it will have the same slope. So these two lines will be parallel. All right, so in other words, the slope between the endpoints on the interval should be equal the slope of the tangent line for some value c, where a is less than c is less than b. So c will be between them, not on the endpoints. All right, so first some examples. Does the mean value theorem apply? Why or why not? So we're going to check these two conditions. So is f continuous between 0 and 4? So continuous on 0 to 4. Well, it's the absolute value graph. It's just going to look like that. That's continuous, so that checks out. Is f differentiable on the open interval from 0 to 4? Well, right at 2, we're going to have this corner, and we are not differentiable at the corner. So we're going to say no. So the mean value theorem does not apply. So we have no MVT because it's not differentiable. All right, next up, g. Let's switch colors here so we don't get mixed up. So g of x is x to the 1/3 on the interval from -1 to 1. So is that a continuous function on the interval, the closed interval from -1 to 1? Well, we can plug in any number here. It's just fine. There's no holes. There's no jumps. There's no vertical asymptotes that I know of. So yeah, that guy's continuous. Is it differentiable on the interval from -1 to 1, not including the endpoints? Well, one way to check is to just take the derivative. So g prime is 1/3 x to the -2/3, or 1/3 cube root of x squared. All right, so now I do notice there is a problem here. We have a problem when the bottom equals 0. All right, so the bottom can't equal 0. That means x can't equal 0 because it's not differentiable at 0, and 0 is in the interval. So this is a no. X equals 0, f prime does not exist. All right, so no MVT for this guy. Shucks. All right, let's take a look at the next one here. H of x is 1/x on the interval from 0 to 2. So is f of x, I guess we're not f, we're h. And the last one was g. Letters are hard. I can do math, just words. H of x continuous on the interval from 0 to 2. All right, so where is this guy not continuous? Well, at x equals 0, we have a vertical asymptote. That's not continuous. That's the endpoint. This includes the endpoint. So this is a no. We've got a vertical asymptote at x equals 0. So no MVT here. We don't even have to check the other one. Doesn't matter as long as if it's not continuous, we're done. Last one here, k of x. Let's see, what color haven't I used? Purple it is. K of x is sine of x on the interval from 0 to 2 pi. So sine of x is continuous. That's never a problem. He's always continuous. He just kind of smoothly goes back and forth. And sine has a nice derivative. Its derivative is just cosine, right? K prime of x is cosine of x, which is perfectly fine everywhere as well. So it's differentiable on the open interval. So yes to the MVT. So the mean value theorem works here. So we could do it if we wanted to. All right. So we would just say that k prime of c would equal the original function at b minus the original function at a over b minus a. This is 0. This is 0. So the top is 0. The bottom is 2 pi. So we're just saying that the derivative equals 0 somewhere. Well, the derivative of cosine of x does equal 0. It equals 0 at pi over 2 and 3 pi over 2. So we get 2 values of c. All right. All right, so more practice. Given that f of x is 5 minus 4 over x, does the mean value theorem apply on the interval from 1 to 4? So this is not continuous at x equals 0, but 0 is not in that interval, so that's not a problem. The derivative, so let's see, so we want to say f of x is continuous on the interval from 1 to 4. That checks out. And then we want to check, is it differentiable? So we're going to take our derivative. F prime of x is, that's going to go away. We can rewrite this as 5 minus 4x to the negative 1. And then we just bring down the negative 1. So we'll get negative 1 times negative 4 is 4. X to the negative 2, or 4 over x squared. And again, the only place this has a problem is 0. 0 is not in this interval. So we can say that f is differentiable on the open interval from 1 to 4. So both of those check out. So the answer to this question is yes, the mean value theorem applies. So now we want to find all values of c that satisfy the mean value theorem. So now we want to say, okay, the derivative then at some c will equal f of 4 minus f of 1 over 4 minus 1, the slope between the two endpoints. So f of 4, if we plug in 4 here, we get 5 minus 4 over 4. So 5 minus 1 is 4. If we plug in 1, we get 5 minus 4 over 1. So 5 minus 4 is 1 over 4 minus 1. Well, that's just going to be 1. So we want the derivative to equal 1. Well, we found the derivative. The derivative was right here. So we set 1 equal to 4 over x squared. Multiply that up. We're just cross multiplying basically. And we're solving. So we get x equals plus or minus 2. All right, but our interval is just from 1 to 4. So the minus 2 we don't care about. We just want x equals 2. All right, or we could say c equals 2. I guess we were using c here. All right, so either one of those is a perfectly fine answer. X equals 2 or c equals 2. There we go. Would the mean value theorem apply in the interval from negative 1 to 1? Well, no, it would not. All right, it's not continuous. At x equals 0, which is in that interval. It's also not differentiable at x equals 0, but all we need is one of them, and once we have one of them, it's not going to work. So if we're curious, here is the graph. Here's our point 2, 3, where it has the same slope as the blue line here. So the blue line here is the one slope, the blue line here is the slope at that point, and the black line here is our curve 5 minus 4x. And you can see, yep, these two blue lines look exactly parallel. This strip stays the same width. All right, so applying this. All right, let's see if we can catch a speeder. So when a truck drives past a parked cop car on the side of the highway, the cop finds the truck is going 50 miles per hour. All right. A second cop car is parked 5 miles down the highway. After 4 minutes, the truck passes the second cop car going 55 miles an hour. Did the truck speed if the speed limit is 65? Well, when he passed both the cops, he was going well below the speed limit, so it doesn't look like he was speeding at either one of those endpoints. But maybe at some time in between those two times, he was going faster. Maybe he does what I do, and when you see a cop car, you slow down so they don't pull you over. All right, so let's see if we can come up with, turn this into the language of a function. So let's say we have some position of his car. Let's just do p of x to be the position of the truck at time x, and that we probably want to do that in hours because we're doing miles per hour. Okay, so let's see. At the beginning, we'll say at position 0, he passes the first cop car, and we'll call that 0. And then 4 minutes later, so again, we want that in hours, so that's going to be 4 over 60 hours. He's now passing the second one 5 miles away. So we've got these 2 points now. All right, now his position, it's continuous on the interval from 0 to that 4 minutes, 4/60. All right, there's no way he can teleport from one spot to another spot. He's got to go from point A to point B, and there's no way he can jump or move or leave the road or, bounce off over here and then magically appear on the other side. So it's continuous. That checks out. Is P of x differentiable on the interval from 0 to 4/60? Well, the derivative of this would just be his speed. P prime will be the velocity. All right, so he always has a velocity between these two cop cards. So yeah, that checks out. So the conditions are met for the mean value theorem. So we'd say by the mean value theorem, we've got the position at 4/60 minus the position at 0 over 4/60 minus 0 will equal the velocity at some point, or in this case, I guess they're calling it the speed, at some point C. All right, so the position at 4/60 is 5 miles down the road. The position at the start was 0. We're dividing by 4/60. So we get 5 times 60/4. 60 divided by 4 is 15. 5 times 15 is 75. And this was in miles on top. This was in hours. So this is miles per hour. So at some point between, so this is for 0 is less than C is less than 4/60. So for some C in between time 0 and that 4 minutes later, he's going 75 miles an hour. All right. So that's probably the average speed on that interval, actually. So he's definitely speeding at some point. So yes, the truck is speeding. At some point. We know it for sure. Mean value theorem tells us it's happening. So we can give him a ticket if we want. All right, so that's the mean value theorem. That's how that works. And Rolle's theorem, just make sure you're checking those conditions for the mean value theorem, then find the slope, set it equal to the derivative, say it exists. You actually usually don't have to solve for it. You just have to say it exists. All right, so that's the end of 3.2. There's no 3.2b. That's just it for 3.2.